Hello and welcome back to Algebra, the video series where we talk a lot about algebraic structures like groups, rings and fields. And indeed, today's part 18 is still about group theory, and our goal is to explain Lagrange's theorem. And in order to do that, we first have to explain what right and left cosets are. However, as always, before we start with the definitions, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download a lot of additional material like quizzes, PDF versions and books. Now for the start of this video, I want to remind you what we have already discussed in part 13. There, we've considered a group G and a subgroup U in it. In fact, such a subgroup can be big or small, but it definitely contains the identity element. Moreover, we have learned that for each subgroup U, we can form conjugate subgroups. This simply works by putting an element G to the left and the inverse of G to the right hand side. Then the result is definitely a subgroup again, and we speak of a conjugate subgroup. And in fact, it could happen that both things describe the same subgroup, but if they are different, we still know they have the same order. So we cannot change the size with this conjugate operation, and we also already know that we get an equivalence relation on the set of subgroups of G. However, one disadvantage we have here, namely for abelian groups. There you can see, no matter what we do, the conjugate subgroup is always equal to U. In contrast to that, what we do now is also interesting for abelian groups, but we will formulate it in the general case. Namely, we will form GU and also UG. These are definitely well-defined subsets in G, but they don't form subgroups in general. So this is the price we have to pay here, and then we will speak of a left coset and a right coset. Usually one can just concentrate on one of the two possibilities because they do essentially the same thing. Most importantly, they also give us an equivalence relation and now directly on the group G. So let's put this immediately into a definition, and the assumption is just that we have a group G and a subgroup U. So the idea is that every subgroup U defines an equivalence relation on G. Therefore, a good notation for that could be tilde with index U. And now by definition we say that two elements from G, called A and B, are equivalent if the combination A with B inverse lies in U. Now that this is in fact an equivalence relation on G is quite easy to check, because we just have to show the three properties. So it should be reflexive, symmetric and transitive. And there you might already see that we have these things simply because U is a subgroup. So the identity element is in U, every inverse of an element in U also lies in U, and if we combine two elements in U, we get an element in U again. So quite easy to check, but please write it down if you don't see it immediately here. Now in order to illustrate that, let's look at a common example. Let's simply take G as the integers together with the addition. And then we already know a subgroup U can be described as MZ. So these are only the integers that are multiples of a given natural number M. And with that it turns out that we actually already know this new equivalence relation. We see that because by definition A and B are equivalent if A minus B lies in U. So please note, in the additive writing, B inverse is equal to minus B. So in other words, we have here that the difference has to be a multiple of M. And indeed, this one we already know from part 8, it's the modulus calculation in the integers. And the common way to denote it is to say that A is given as B mod M. In other words, now you could say that this common modulus equivalence relation is generalized in our concept above. This means we have a classification like this one for an abstract group G and a subgroup U as well. Therefore, let's immediately look at the corresponding equivalence classes for this equivalence relation. This means if we take any element lowercase g from G, we look at all the other elements in the group which are also equivalent to G. So as always, this equivalence class has to be a whole subset in G. And formally we would just write take all the elements A from G that satisfy that A is equivalent to our fixed G. And by definition we already know what it means. It simply states that A times G inverse lies in our subgroup U. And on the element level, this just means that there exists an element U in our subgroup U, such that A combined with G inverse is equal to this U. And indeed, if we write it like that, we can just multiply with G on both sides. This makes it simpler because it removes the inverse from the equation. And moreover, we also see that every A has the form U times G, which simply tells us that the whole equivalence class can be written as the right coset. So in short, we just have capital U times G. And there you might believe me that by defining the equivalence relation with the inverse on the left-hand side, that we get the equivalence class as the left coset. Hence, in total, we just get that the right cosets and the left cosets can be written as equivalence classes. And therefore, the general theory of equivalence relations immediately gives us the following result. Namely, G can be written as the disjoint union of the equivalence classes. So in our case, we can say we go through all the elements lowercase g and then form the union of the right cosets. However, here please be careful. If you use two different elements G1 and G2, you could still describe the same equivalence class with it. However, this is the only possibility where the two right cosets are not disjoint. Indeed, two different equivalence classes cannot have any element in common. And now similarly, as already said, you can also state the whole thing with the left cosets. And since it gives us exactly the same description of G, one usually would just choose one of them. So for example, let's choose the right cosets to illustrate everything in a picture. We could say that this thing here is our group G, and inside we find a subgroup U. And now for example, a right coset could lie here. And now we know if it's not equal to U, we have a disjoint set. And now indeed, the correct picture is that we have a whole decomposition of our group G. And moreover, every right coset that is included here has the same size as our subgroup U. This is quite simple to see because you can write down a bijection F. This means we go from UG1 to UG2. And obviously every element on the left-hand side can be written as lowercase u times G1. And since this U is definitely uniquely determined, we can just use it to describe the whole map F. Namely, we map it to UG2. Hence, by definition, it's already surjective. And it's also injective because if we map at the same element, then the inputs UG1 and U tilde G1 have to be the same. We immediately see that because we have the equality UG2 with U tilde G2. So multiplying with G2 inverse, we get that U is equal to U tilde, which just states that the input was already the same. And now since we have a nice bijection here, we know that the sizes of the two sets left and right are actually the same. Hence, if we write the cardinality with the vertical lines, we get UG has the same cardinality as U. And moreover, the same also holds for the left cosets. And most importantly, this equality holds no matter which element G we choose from the group. So please remember that the sizes of the cosets are all the same. And this nice fact we can use in the next video when we start with Lagrange's theorem. So I really hope I meet you there again and have a nice day. Bye bye.